Okay, so I am going to discuss this paper. So first off, thanks for inviting me here. Coming from Wisconsin to Oregon, I put up the basketball picture, not the football picture. So I want to thank Bruce, and in particular Bruce, for getting me here. So this was an interesting paper. There's a lot in it, which Inku only sort of touched on. I'm going to have a slightly different interpretation of some of their results, some of which I think sort of came up in some of the discussions so far. So I want to think about learning and model averaging, which Inku talked about. So we think of sort of the classic learning model, starting with Bray, Marcet, Sargent, Evans, and Hunkapoya. Those all used recursive least squares, providing conditions where beliefs are going to converge over time to rational expectations equilibrium. And underlying this is the assumption that there is some constant parameters out there, which are the truth that you're learning. And as you get more and more observations, you're just getting more samples on the same underlying truth. So the weight on new observations is going to go to 0 as t goes to infinity. A lot of recent applications in learning literature, which we've seen several of, focus on constant gain learning or perpetual learning. And one justification of that, and that's the justification which is referenced in the paper, is that agents suspect parameter drift. And as we've shown, and in some work with George and Seppo, and some other work with Tom also, we looked at constant gain recursive least squares as approximately a Kalman filter for a random walk-in coefficients model with a very particular prior. So a coefficient drift of a particular form. Okay, and so sort of in practice what they do in the paper is, well, what if agents mix between, put some probability on there being a constant parameter model, the truth being a constant parameter model, some probability on the truth being a time-varying parameter model, and then they're going to update the weights on the model over time. And then the question is, will beliefs, so the estimates under each of the models, will those converge, and will the probability weights converge? And as agents learn, so this is a lot of abbreviations here, but there's a lot of insiders in this literature here. So what's going on is that as agents learn, the actual law of motion is drifting. Right, so that's part of my difference in interpretation between what Inku said about things being correctly specified and misspecified. When the data generating process is endogenous, a constant parameter model is not really correctly specified. It's only in the limit is it correctly specified. Right, through the usual T-map, your beliefs, or the underlying parameters are actually drifting, but in the limit they're not. So then the question which they focused on is, will agents eventually learn the correct model, which is constant? Okay. So what we did with George and Seppo and Tom in this, Inku was nice and pronounced all of our names instead of Evans et al. I don't know if any of you saw there was a paper, there was an article in the Wall Street Journal last week about this guy, George Odd, who works at CERN, who has, he's published over 458 papers in the last decade. And why is he so famous? His name is AAD, right? And so one of these papers had over 5,000 authors on it. So it's 24 pages of just authors, but it's referred to as Odd et al, right? So I'm thinking of changing my name from W to something else. Okay. Anyways, what did we do back then? Well, we looked at this question in a particular framework. We looked at using the cobweb model. We ran some simulations and documented some results. What we were focusing on, one of the things we focused on was the importance of the strength of the feedback. How important is the sort of self-referential character, which is something I'll come back to here. These were all the bullets from our paper, which I cut and pasted. So what did we find? We found convergence for a range of parameters in which the expectations, the influence of expectations is not too strong and positive feedback. And it has to be less than 1 for 1, right? So with just like in least squares. We can have convergence to the time-varying parameter model, even though the prior puts an atom on the rational expectations model. And that happens when we get, again, sufficient feedback. And what we found is, we look at model averaging, but at the end we get sort of a selection, right? So I say we find all these things. What we found, how did we find them? We ran some simulations and showed that this is sort of what resulted. And so these are some of the simulations, right? So this was our model. And so the strength of the feedback is this alpha parameter. And so this was from running a whole bunch of simulations. 10,000, good, I wrote it there. This is as we vary alpha. Same numbering here. Model 0 is the constant parameter model. Model 1 is, which is in blue, is the time-varying parameter model. And what did we find? Well, as the strength of feedback increases, you're more likely, what's plotted here, the fraction of the number of simulations which are converging to each one. So with very low feedback, you tend to converge to model 0, the constant parameter model. As the feedback increases, you converge more likely to the time-varying parameter model. But then when things are nearly 1-for-1, it's basically 50-50. So that's something we documented. Had some speculations as to sort of what's driving things, but we didn't work out any theorems. This set of simulations is closer to what they sort of established. This is saying, okay, so we got this. I didn't write the 1 there, but the beta 1 model is in agent's head is this random walking coefficient. Slightly different notation. We had this sigma beta, which is the standard deviation or the innovation in this random walk. What happens as you shrink that? And this is the percentage of simulation runs which converge to model 1. Well, you can see it's increasing. Looks like it's decreasing, but that's only because this was for 40,000 simulation, 40,000 periods. If you run it out to 1 million periods, you're finding more and more. So it just takes longer as the innovation, as the volatility of the innovations decreases, you get more convergence to the time-varying parameter model. Okay. So that's what we showed by simulations. And what do Inku and Ken do? Again, in a slightly different model, but essentially the same type of thing. They analyze the belief dynamics, and where we had simulations, they've got some propositions, right? Which is that's a big contribution. There's a little bit of caveat. I think the proofs are a little bit talky, but nonetheless, this was really a nice result or a nice paper. I played around with doing these multiple timescale limits, but I sort of gave up on it. They do it, and if you've looked at the paper, what's sort of interesting is it's not just multiple timescales, but there's multiple timescales. So there's four different senses or speeds in which things are evolving. And so what does that mean, a timescale? It's essentially, if something is evolving fast, you can sort of average that out. If it's slow, you sort of treat it as constant. All right, so when you're analyzing one piece, you have to have a piece of the model where you're thinking about the parameters within the model or the weights over the two models. It's an issue of what are you treating as constant versus what are you averaging over. And so they have 4 different timescales. The data is sort of the fastest. The time-varying parameter model, since that's drifted around, is slower than the data, but faster than everything else. The constant parameter model, since that's sort of slowing down over time as you get more observations. And then the model weights, and so you're then mixing between the two. So that was, Inku didn't talk much about the analysis, but that's sort of what's underlying their results. And what do they show? Well, you get convergence of beliefs, to the rational expectations at either model 0 or model 1. As t goes to infinity, that's really sort of for that, and as the innovation variance shrinks. And they establish the convergence of the weight, the model weights, the pi's, to a neighborhood of 1 as t goes to infinity and as the innovation variance shrinks, and they have a particular way in which they're shrinking that due to the time scales. All right. The main idea is that they show that it's easier to escape from the constant parameter model than from the time-varying parameter model. which is, in some sense, it's reminiscent of some of the sort of older literature, evolutionary games. You sort of think about equilibrium selection. You think of how easy is it to move from one equilibrium to another. And the equilibrium which is hardest to get out of is where you end up spending more of the time. But the argument is actually rather a little bit different here. The idea is roughly that if agents believe in the time-varying parameter model, then they're going to get some shocks, and it's not going to be likely that they're going to switch. On the other hand, if they believe in the constant model, well then if they get some shocks, especially early on in a sample, then they're going to switch. Right? So over time, the constant model, we're getting less and less drift. But if we get some shocks, especially early on in a sample, then we're going to switch from believing in the constant model to believing in the time-varying model. And for small innovation variances, this switch is more likely to happen. All right. So one interpretation of this, which Inku emphasized, is sort of the negative one. Oh, sorry. So the result was, we get convergence in an appropriate sense to the time-varying parameter model. So Inku talked about, crazy people and stuff, and this is sort of saying that people can't learn the rational expectations equilibrium. Another way to say that, another interpretation of that is, hey, a lot of us like working with constant gain models. This gives us a rationale for doing that. Right? Gives us a better shot at explaining the data. We can have interesting dynamics. So I don't fear the non-convergence. Embrace it. Right? It justifies using constant gain learning. As long as we've got a non-zero prior, that's what agents would actually choose. A little bit on, OK, so comments on the paper briefly in my remaining 7 minutes.
Yeah.
3?
You could have 2.
OK. I thought the tone in the paper was a little strong, some of the statements. Talking about, this one was sort of interesting. The debate is largely academic since the problem is the model fails to explain the data, and then they go on and prove 4 time-scale results. So I was complaining a little bit about tone. And then we were talking about crazy types. And somebody who's been criticized for his tone is certainly a crazy type. So forget about tone. We don't have time for tone. Let's actually look at some of the results. So the question is, can there be consistency between beliefs and outcomes other than rational expectations equilibrium? And so this is something which we've sort of highlighted or thought about. Is the self-confirming equilibrium is the limit, but we always have, both of these models are misspecified in some sense. So thinking of one is the correct model and one is the wrong model, I wasn't necessarily that happy with that interpretation. What does it mean to be misspecified? Sort of in the limit versus on the transition, but we're taking large time limits and small gain limits or small innovation variance limits. So in that limit as well, we're not misspecified. So it's sort of a subtle question there. Same thing here. What does it mean? To focus on, well, they don't learn the rational expectations equilibrium. Well, their beliefs are converging. They're converging in distribution. That distribution is collapsing. I would say that's learning it, but that's a question of what does it mean to learn it, which I don't necessarily have an answer to. What's sort of interesting comment or something which I discovered was this selection result, I think, is a little bit less strong than it appears. So if you look for moderately small sigma v and look at the dynamics over time, it's not that over time you're going to be converging to putting probability 1. You converge to, what you actually find is you converge to 1 or 0. And the likelihood in which you converge to one or the other is going to depend on how big the parameter drift is. So it's not over time, eventually agents can't learn, but there's a chance that they're going to learn. There's a chance that they're not going to learn the rational expectations equilibrium. The chance that which they're going to learn is going to increase as the probability, or as the innovation variance shrinks. So it's not really an issue of the time scale, but of the drift scale. How big is that innovation drift? And so for small sigma v, you get a chance to escape before getting locked in. So let me just show a couple of pictures there. So this was with us, I don't know what's big or small, but this is a pretty small sigma v. Here we're getting sort of the beliefs under model 0 and model 1. So this is just in a cross-section of them and thinking of 10,000 periods. And this is what's happening. This is sort of what I would just want to focus on. So we're getting like 65% of the time you're converging to model 1 out of these 10,000 simulations. And this is what's happening to the time path, right? So there's some shakeout early on, but then eventually you're either going up here or down there. But then even when you're down here, you're locked in, right? So at least, I ran this on for a long time. I stopped this one at 100,000, but last night I kicked it off before dinner and ran it on to 10 million and still never observed, of these sample paths here, you never get back.
Sorry, is this the Williams et al. Model or their model?
This is their model. So what's happening? So the way to read the convergence result of the long-run selection result
We're all figuring that out.
is that as sigma v shrinks, it's taking longer to sort this out, and you're getting more mass up here. Okay, but it's still you're getting. And why are you still getting some people locked in there? Well, there's sort of a race between, if you're in this model, your gain is going to 0. The probability of escaping is going to 0 as time goes to infinity. So there's sort of a race. I know I'm negative, yeah. There's a race between these initial shocks and being essentially locked in. So if you get big enough shocks early on, then you can get away from it. All right. Let me just plot one last picture. Something I noticed, it doesn't actually look like beliefs converge here, which is something just I'll throw out there. It probably happens in our model as well. The self-confirming equilibrium is 1 here, and it doesn't look like you're converging to 1 at all. So I don't know. That's a question for the authors and something I'll have to look at as well, since it's in our paper as well, is the beliefs don't actually appear to be converging. So there's some questions there. Overall, excellent paper. I'm way out of time, so